Good afternoon. This is Lab Group 3 from EEL3310 C. This is the lab portion. Lab number 2, Introduction to Kirchhoff's Voltage Law, Current Law, and Superposition Theorem. My name is Colton Falusi. Number Colton Falusi is 637-6474.
I'm Jose Hernandez, 616-9293.
And my name is Mr. Briceno. It's 608-6235.
All right. So we're going to jump right in. I know last week we kind of took a little bit extra time, so I want to make sure we're cognizant of our time this week. Activity 1, we're just going to be confirming KVL, KCL, and activity 2, we're going to be confirming superposition theorem for the same circuit. So I think, guys, this part 1 really helped with part 2, at least for me, and I think for you guys as well, because just being able to have the data from KVL, especially knowing how much current is going through each element, then for superposition we can kind of choose which element we want to use to verify the superposition and make it a little easier on ourselves, right?
So we have the currents, the voltage is flowing. We're trying to use KVL verification to find the current flowing in the loops. We go from the left side. We're going to clockwise formation, sorry. And we have the -7 from the main source 1, the voltage there. So -7 because we're going against the current of the loop. Then we have the voltage in, going on from resistor 1. It's going to be -3 as well because we're going against that. And then we have the positive because that's the one we start with pretty much in the reference 3 of the volt through resistor 3. So that's 10 volts there. Adding up to 0, of course. And then the same thing with the right side, clockwise formation. And you have the same thing following up. A lot of these go in the same formation as the current loop, so everything comes out okay. If I'm not mistaken.
Yeah, absolutely.
Yeah,
very good, very good. Yeah, because if you look on the top loop, exactly the same thing, and outer loop, just for fun, since you got both sources there, you can consider kind of one source to be as a negative, one as a positive, because they're going opposite directions when you think about that. And then what do you guys think about KCL, confirming that through the simulation? I mean, we could, if we wanted to, we could confirm these nodes on the left and right as well. Because I mean, the simulation data shows it right here, right? You can see that you got 1.3 milliamps coming in from the top, you got 3 milliamps coming in from the right, and then you got 4.3 coming down from the bottom. So
yeah, we got 3 of them, but
KCL checks here.
flowing, yeah.
Yeah, I mean, you could do the bottom node too. I didn't even think about that one, right? Like, you got 4.3 milliamps coming in from this side here, 2
left,
milliamps coming in from the top, and then
6.3
6.3
right.
leaving. So simulation checks out. Looking at the math, the way that I thought it would make most sense would be, we're thinking KVL, we're going to do just big I1, big I2, big I3. And then of course, if we're considering the current through each resistor, we'll notate that as big I through resistor 1, big I through resistor 2, etc. So with that notation, then we can see, of course, right, that, for example, this IR1 would be equal to I1, since this is going positive and opposite direction of I3. You could say that the current through resistor 1 is equal to big I1 minus big I3, something like that. So that's kind of what we did here for our KVL. Of course, Dr. Vlasov gave us these top 3 equations. Thank you, Dr. Vlasov, for the top 3 equations in the office hours. So that was something that we were able to start with for the KVL for each of the left loop, the middle loop, the top loop. And then of course, when you plug in from there, it kind of just ends up as a 3x3 matrix to allow you to get those big I values. And then, as we said, we can find the current through the resistors by doing, I1 minus I3, I1 minus I2, etc. Then we have the check marks here just to point out that the values that we're finding are equal, in fact, to the values from the table in the simulation.
Yeah.
Certainly. And then we wanted to find the voltage through those elements too, right, guys? I thought that would be kind of something that would be important. So when we have those currents through the resistances, then we already know the resistance that's given. So, Ohm's law tells us, of course, we know that voltage. And then it's nice to see that voltage check out to the same voltages that we see in the simulation as well. Yeah, absolutely, because then we're already getting these current values from doing all that work verifying the KVL. We might as well use those to verify our KCL. So we see, okay, we know for a fact now the current going through resistor 1 and the current going through resistor 3, if you combine those together, it is equal to the current going through resistor 2, just as you see in that simulation, right? And moving forward now, you see we're already going to be using this for part 2, right? We've got superposition, which helps us now, because like the way that we want to confirm it is say, okay, now we know for a fact that the current or voltage across a given element when both sources are there is equal to something. And for example, and I'm kind of jumping ahead here, but I would say that the current, for example, going through resistor 4 when both sources are present is equal to 1.3 milliamps. So in order to verify superposition, what we could do is take away each source individually, right? Find out what that current is going through that element when each source individually is there, and then combine those and see that, okay, absolutely, yes, when you combine those, it is equal to that response when you get both of them there. And I think that even before going through the math, just seeing the results from the simulation of the superposition principle is very, very interesting, and it's kind of even more powerful than the math that, because I mean, I'll be honest, and I don't think anybody's going to go and confirm the superposition principle for each element of the circuit. I mean, it takes about a page of work to confirm it for one
Yeah.
element of the circuit. So I think that when you get to see it confirmed for each element of the circuit side by side and say, okay, look at the response from when source 1 is removed, look at the response when source 2 is removed, you take each of those values, add them together, and you get the response when both sources are present. That's a very, powerful illustration there. I thought, if I was going to choose one element, the element to choose that would make most sense would be resistor 4, because it's kind of off on its own. So the best way to do that would be, I thought, a current split, because, right, guys, we want to make sure that we know exactly the amount of current going through that branch specifically. So if we don't have, for example, the 7-volt source there, we only have the 20-volt source, then we can go ahead and clean up all that stuff on the bottom, right? Once you get rid of one of the sources, and you can see it on the other side too, if you get rid of this source instead, then you have these two that are in parallel. You can, create that as a equivalent resistance, then put it in series with your one here, which will bring you down to just that 2 in parallel. So you've got the 2 in parallel with just the 20-volt response and then the 7-volt response. So you can see here that, and it's also notable, right, that you've got kind of the way I noted it was I sub R4 being, coming out of the battery, out of the positive terminal of the battery. So it's going to be kind of going opposite directions into the resistor each time. So if you look at when we're talking about the 20-volt source, IR4 is going in from this side, and we got 2 milliamps. On this one, it's going in from the opposite side, and we got 0.7 milliamps. So we don't want to add those up because they're coming in from opposite sides, right? Yeah, that was a very interesting lab this week. I think we
That
learned a
was
lot here.
pretty good, yeah.
Yep. Well, all right. I think that's pretty
It was a
much it.
pleasure.
Yep.
Yeah.
Looking for the stop recording. All right, signing off, guys.